Thank you, Bill. And thank you to the organizers, both for a wonderful conference so far, but I was more difficult, I think, than most of the participants in just arranging my time here. So I appreciate all the work you did with me to make this possible. And I also want to say I was very impressed with one thing yesterday. Doug's record of almost a publication a month. That, for over a 40-year career, that's unbelievable. So congratulations on that. That's really terrific, and that's the reason why we're here celebrating that. So well done. You will notice, if you look at the program for this session, that's not the title that I have listed. In fact, my title has linking systems of different sets and partial different sets listed, but I'll get there. I just want to get there by going through my view of how different sets are built, and a lot of this is going to overlap with what Jonathan was talking about, okay? But you might think of this as almost an impressionistic painting, that we're going to look at things like this. So if you go back to the early 70s, one of the constructions that Jonathan talked about, he didn't use the word McFarland, but Bob McFarland in the early 1970s used hyperplanes of vector spaces over finite fields. So what I want you to think about when you look at this is that's a Venn diagram of hyperplanes. So each one of those petals is a hyperplane. They intersect. So, you know, a hyperplane is just a one dimension less than the full vector space subspace. And they overlap. If you want a particular one to have in your head, because this is what we're going to use a fair amount of, think of the vector space of dimension 3 over the field with 2 elements. Zeros and ones, there's only 8 vectors. The hyperplanes are the subspaces of dimension 2. There are 7 of those. Well, this one has 9 on it, but just imagine there's only 7 of those. Those hyperplanes are going to intersect. And what McFarland recognized is that he could start with that collection of subsets and then have another group that he would use just as coset representatives for the hyperplanes. So he would have a group of order 8, and in fact, he could use any group of order 8, 7 hyperplanes over here, just attach a group element to a hyperplane. That always gives you a different set. That was a great insight, okay? And a lot of work in different sets up to that point had been in cyclic groups. Now it expanded into non-cyclic groups, and in fact, in groups of order 64, since there are 5 non-abelian groups of order 8, you had 5 choices for this. This had to be the elementary abelian group of order 8, but you get different sets in 5 groups out of 267, as Jonathan was mentioning. And when we go up, that gets you 14 different sets in groups of order 256 out of the 56,092. And if we go up to 1,024, you get 51, because there are 15 non-isomorphic groups of order 32, and you just attach them to the appropriate vector space. This got things off the ground, but it's this hyperplane that's underlying all of those different sets that we're talking about. Roughly 10 years later, John Dillon came along and said, you had those separated. You had a elementary abelian group here, and then you could put any group you wanted on the other side. Why not overlay them? So if you look inside here, you can see the McFarland underlying it, and we're just putting something else on top. Those coset representative assignments could come from the factor group or a transversal. So no longer do we have to have the vector space separated out. we can look at a lot of groups as long as they have a normal elementary abelian subgroup of the appropriate order. Okay, now that may or may not seem like a big deal to you, but instead of only having 5 subgroups of order 64, we now have about 230 groups that have a different set using this construction. That's pretty impressive. And when we go to the bigger groups, you get 39,000-ish. And we don't know in the groups of order 1024, as Jonathan was saying, there's a lot to be discovered in that. We could probably get some ballparks there, but for now, just realize that's a massive expansion. The one thing that didn't get, and Jonathan mentioned this in the talk, if you think about C8 by C8, group of order 64, 2 cyclic groups of order 8, you don't have a subgroup C2 by C2 by C2. The rank of that's not big enough. And so McFarland or Dillon's generalization of that isn't going to cover that. We need something else. Oh, actually, so here's just if you want to see some details on how to build it, here's C2 cubed, and there's some groups. But if you go to C8 by C8 and groups like that, you're going to need something a little bit more than just the hyperplane construction. And this is intended to impressionistically be a little more general than hyperplanes. You get what we called covering EBSs, extended building sets is what it stands for. And there, the pieces, those petals of the flower, aren't necessarily subgroups. In fact, they generally won't be, but they have enough structure to them that we can control what's going on. Okay, and just to sort of summarize this part of it, the history lesson, Kibler in '78 wrote a paper that a lot of us older folks worked with because he wrote out explicit difference sets in all of the small groups up to, I forget what the size was, but in particular, there were all the groups of order 16, and of the 14 non-isomorphic groups, excluding cyclic and dihedral, all the others have a different set, and he wrote them out. Okay? That was great just for getting your hands dirty and seeing what was going on. Dillon in the early 90s and lots of other people were involved with this, went up to the groups of order 64, applying the things that we're talking about here. And then, as Jonathan was talking about, Taylor Applebaum and the 8-author paper did groups of order 256 with some new insights. But the point of this history lesson, and I am going to get to the other parts of it here in a second, but the point of this is as we learn about some combinatorial structure, we get some key insight, but then, at least in 2 groups, people pushed it out and found other things that were more general that handled lots and lots more cases. In general, the way, or a simple way to write this down, is to say that the set D is going to be some union of a coset representative, and you can think in terms of McFarland, that came from one group over here, with some nice geometrical object, could be hyperplanes, or if you go to covering EBSs, that would be blocks. Here's the transition for today. I want to think of those B sub i's as linking difference sets. Now, I haven't told you what that is yet, okay? But I'm just using the same framework that we've done within difference sets and replacing the B sub i's with some other object that we can control fairly well. And here's what I mean by control, okay? If you are working in the group ring, and this is one of the standard ways that people in difference sets work, that D is that union of G sub I, B sub I, And we want to do D times D inverse. And so you're going to have, you can break that sum up into the internal differences and the external differences. What I mean by that is you're going to have some G sub I, B sub I's that match up with G sub I, B sub I's here. I call those internal differences, and then you'll have some G sub I, B sub I's that match up with G sub J, B sub J's over here. And you need to be able to say something about each of those pieces. If those B sub I's are themselves different sets, then the internal differences are taken care of for you. That part is very nicely controlled. So it's those external differences, what's happening between the B sub I's and the B sub J's. That's the linking property. And just a quick story about this. I didn't know anything about linking of designs until Bill Martin came to a conference in Richmond, Virginia, and challenged the different set community to find different sets, collections of different sets that satisfied this property. He had an association scheme reason for that, and he had some small examples of that. Some of us took up the challenge and together with Bill wrote a paper where the linking property of different sets turns out to be different sets that satisfy that equation in the middle of this slide. The external differences, D sub I times D sub J inverse, will give you a third different set, a D sub K, some replication number, a lambda, and then the complement of that will be mu, is the letters that we use. But if you go back to this equation, that means that we have control over those external differences. Okay, and that's exactly what we need in order to construct. Here's the other part of the title that I haven't told you about. Partial different sets are very similar to different sets, except you don't have the same covering number for all of the group elements. Some of the group elements are covered one number, usually it's going to be a lambda, and the other is going to be a mu. I've drawn this picture, even though it's not of the family that I want, but it's a strongly regular graph. When you get a partial difference set, it's a regular automorphism group of a strongly regular graph, and you get lots of other things. So partial difference sets are by themselves very interesting, and it's, you know, for that equation that I showed you, you've got those two replication numbers. That linking property is going to be at least one way of thinking about how we could go about doing this. Now, here's the particular example that I want to focus on. Denniston, I think it was in the 60s, I don't remember the exact date, but Denniston was working in projective geometries, and he was looking for projective sets, which are projective points that have two intersection sizes with hyperplanes. That is a partial difference set. So when you extract what Denniston did, he found, and I wrote it small, you don't need to know the details, but he found partial difference sets with those parameters. If you plug in m equals 3, the size of the group is 64, the size of the subset is 18, I'll come back to that in a second, and the replication numbers are 2 and 6. Okay? Now, I said the 18 is what you want to focus on because your 8-year-old could help you to construct different sets. Here's a key observation. 18 is 6 times 3. Why is that important? The 6, if you remember, was the size of a different set in a group of order 16. And so what I'm going to look for here is 3 linking different sets that I will attach coset representatives to, and then work through the algebra and see if we get a partial difference set with the 64, 18, 2, and 6 as the parameters. But a lot of that's going to be forced on us just because of the difference set property that we're plugging into those pieces. And just, again, a little history of this. Denniston was doing things in projective geometries. He was using irreducible quadratic forms. But when you go back and you look at what he did, this was 50 years before linking systems were defined, but that's what he was finding, is he was finding linking systems of different sets in elementary abelian two groups. A few years later, quite a few years later, Qing Xiang and I wrote a paper on a construction of partial difference sets using Galois rings. And when we look back at that, or when I look back at that, I see all we were doing is we were coming up with linking systems of different sets and then finding the appropriate way to attach the coset representatives, and all the numbers worked out. I should have mentioned at the start, and it was on my title slide, but Andrew Brady, and I should have the little asterisks on it, like you saw in the previous talk, is an undergraduate, really clever undergraduate. He worked with me in the summer of 21, and he looked inside the groups of order 267 to find 64, 18, 2, 6 partial difference sets. And when he got a bunch of examples of these, I said, why don't you check to see if there's some internal structure? And lo and behold, linking systems were everywhere. Okay, that seemed to be in non-abelian groups of place. Now, they weren't quite the linking systems that I would naturally have thought of, but they were internally in these computer results that Andrew found. So what I really want to have happen is I need to understand linking systems better. There has been some work, actually a decent amount of work, since the original paper on linking systems about 10 or 12 years ago. And so we do have a better understanding of linking systems, but we need to be able to figure out how do we plug those into these non-abelian groups, and what tweaks do we need to make on the linking systems in order to make all the things work out. I've showed the 64, 18, whatever. That's one of the Denniston parameters. There's lots of other Denniston parameters. I think that's a natural place for this linking property to show up. But what I don't know is whether there will be other places where the linking systems could be plugged in place of hyperplanes or blocks like we saw in the covering EBSs to give you combinatorial objects that are really nice. And so I think there's a lot to be done here. This is a very preliminary report on this, but hopefully that impressionistic approach gave you an idea of what I think we have. Thank you.